Hi, it's Mr. Mac. We're going to learn a lot about Einstein's theory of special relativity. We're going to find out a little bit about time dilation and try and work out ways that we can answer questions about special relativity. So the inquiry question is, how does the behaviour of light affect concepts of time, space and matter? We're learning to describe the evidence for, consequences of, and applications of Einstein's theory of special relativity. By the end of this, we'll be able to solve complex questions about time dilation, length contraction, and mass-energy equivalence. In kinematics, we learned about relative motion, where two objects that are moving have velocities that are different, resulting in a combined relative motion. For example, two cars approaching each other on a highway at 100 kilometers per hour have a combined relative motion of 200 kilometers per hour. This idea was developed by Galileo. He stated that measurements of velocity depend on the inertial frame of reference that the observer is in. Galileo published a thought experiment in 1632 about relative motion. Imagine Galileo was sitting in the hull of a windowless ship, unable to see outside. His ship is moving at a constant velocity. At this point, being in the ship's hull will feel as though the ship was at rest in a calm harbour. In this thought experiment, Galileo then conducts simple mechanical experiments, such as simply dropping a ball from the top of the ship's cabin to the floor, noting where it lands. If the ship were stationary at the dock, the ball would drop straight to the floor directly beneath where Galileo was holding it. Galileo realized, even when the ship was moving, the ball would simply fall directly where it's dropped, just as if the ship were stationary. From Galileo's point of view, in the ship's hull, there was no difference between a ship with constant velocity and a stationary one. Albert Einstein refined Galileo's ideas with his theory of special relativity in the early 1900s. An inertial frame of reference is one where no acceleration occurs, thus the velocity is constant. An inertial frame of reference can be assigned to an object. In effect, this object is not moving, but everything else is moving relative to that frame of reference. This object could be the Earth, or a ship, as in Galileo's ship, or a train. Each frame of reference has its own coordinate system with axes and a time. Imagine that a clock is showing the time in one frame of reference. Einstein wondered what would happen if that inertial frame of reference was moving very close to the speed of light. As we think this through, we'll find out that some weird things occur. Einstein assumed just two things. We call them Einstein's postulates. One, the speed of light in a vacuum is an absolute constant, c, in all inertial frames. And two, all inertial frames of reference are equivalent, that is, the laws of physics apply equally. With these two postulates, we have to rethink our understanding of space-time. The same laws of physics apply whether you are standing still, travelling in a car, walking down the aisle of a passenger train carriage, or flying through space. Since one of the laws of physics states that the speed of light is constant, called c, then the speed of light must be the same in every frame of reference. That's pretty amazing. we know that a police officer on the side of the road can detect the speed of two cars, and if one is going at 110 kilometers per hour in a 100 kilometers per hour zone, then the police officer will pull that driver over and fine him or her, even if it was passing another car going at 90 kilometers per hour. Now, the driver in the second car only sees the first car passing at 20 kilometers per hour with respect to the inertial frame of reference of the second car. This is Galilean relativity. The slower driver and the police officer measure different speeds of the first car, which is how we intuitively think. Light doesn't work this way. If you measure the speed of light on Earth as though you were standing still, then you'll find that it is 300 million meters per second, or 3 times 10 to the 8 meters per second. This is true also if you're travelling in a fast train on smooth tracks. You'll still measure the speed of light as 3 times 10 to the 8 meters per second. Even if you're in a spacecraft travelling at 299 million meters per second, you will also measure the speed of light as 3 times 10 to the 8 meters per second. It doesn't matter which frame of reference you're in. It's the same. We can think of the speed of light as a universal speed limit. For a person in a spacecraft traveling at 299 million meters per second and another person on Earth, for both of them to measure the speed of light, it's going to be the same in their own frame of reference. But they must experience time differently. This is the first weird inference about special relativity. Time goes at different rates for observers in different frames of reference. So if time is going at different rates for observers in different frames of reference, time is relative, and it's going at different rates for different observers. So the faster you move relative to the speed of light, the slower time passes. This is what is called time dilation. This brings us to time dilation. Einstein came up with Gedanken, which is German for experiments or thought experiments. Here's a simple Gedanken. Imagine Fred in diagram A. Fred is travelling on a fast train, so Fred fast, at velocity v train. And the path of light on the train goes a distance of w, the width, between two mirrors m1 and m2, at a velocity equal to c, the speed of light. So what is the expression for the time that it takes, t0? Well, using displacement equals velocity times time, we find that the displacement is 2w, twice the width, equals c, the speed of light, times t0. Rearranging, t0 equals 2w on c. Now let's see what's happening from Pierres' perspective. He's standing on the platform, Pierre platform. So Vp equals 0 with respect to the platform, the frame of reference. He also measures the time taken. Both agree that the distance between the mirrors is w, the width. From Pierre's perspective, the light travels along two sides of a triangle since the train is moving to the right, a distance using displacement s equals v train times time. The hypotenuse of one right-angled triangle is half of ct, since t is the same. The short side of the right-angled triangle is vt on 2. So using Pythagoras' theorem, c squared equals a squared plus b squared, and I'm using capitals to avoid confusion. Replacing the hypotenuse, we have ct on 2 squared equals vt on 2 squared plus w squared. So you can see ct on 2 all squared equals vt on 2 all squared plus w squared. Squaring brackets, c squared t squared on 4 equals v squared t squared on 4 plus w squared. Rearranging to get w squared on the right hand side, and then factorising, taking c squared t squared on 4 out as a common factor. Inside the brackets we have 1 minus v squared on c squared. And then let's take the c squared across to the other side by dividing. So on the right hand side it's w squared on c squared. And then taking square roots of both sides, and that's fairly straightforward because t squared becomes t, 4 becomes 2. Everything in the brackets is under a square root sign, and on the right hand side we simply have w on c. Now by multiplying everything by 2 in this to get rid of the half on the left, we now have t square root 1 minus v squared on c squared equals 2w on c. And 2w on c, you may recall, is t0. So t0 is 2w on c. So we now have an expression for t0 and t, relating the two together. And you can see finally, and I've put it up high, t, the time in Pierres' frame, equals t0 over square root of 1 minus v squared on c squared. Let's see how that works out in practice. So here's a worked example. A pilot in a spaceship travelling with a velocity of 0.25 c presses a button to flash a hello sign for 5 seconds at a space station it passes. Part A. For how long is the flash seen by an observer on the space station? And part B. Explain the reasoning. Well, the first step is data. T0, in the frame of reference of the spaceship, 5 seconds is how long the sign flashes hello. V on C, and this is a useful shortcut, is 0.25. And T is what we need to find. So here's the equation. The equation is T equals T0 over the square root of 1 minus V squared on C squared. And that connects the two frames of reference. Substituting, T0 is 5, V on C is 0.25, and you can see it's quite straightforward. T equals 5 over the square root of 1 minus 0.25 squared. And just using a calculator, we find that t equals 5.16 seconds. It's a little bit more. This is dilated or expanded time dilation. The explanation is this. The observer in the space station views the rocket travelling towards it at a velocity of 0.25 c. This, by the way, is very similar to our illustration of Fred and Pierre with the train going past. From this frame of reference, a clock on the rocket will be slow compared to one on the space station. So, observers see any clock or flash as being slow, in other words, taking more time when it's moving relative to their frame of reference. And now you can see the reasoning for why time dilates.